Welcome to this lesson on operations research. Today, we are going to explore a fascinating and highly practical topic known as the minimal spanning tree problem. Imagine you are tasked with connecting several cities to a power grid, and you want to spend the least amount of money possible on cables. How do you do it efficiently? By the end of this video, you will understand exactly how to solve this challenge. Before we dive into the main problem, let us define some basic terms used in network theory. Think of a map. A graph is simply a collection of points and the lines that connect them. The points are called nodes or vertices, which you can imagine as cities. The lines connecting them are edges, representing roads or pipes. Each edge has a weight, which is a number representing the cost or distance to travel across it. A cycle is a closed loop, and a spanning tree is a special set of edges that connects every single node but contains absolutely zero cycles. Now that we understand what a spanning tree is, what makes it minimal? A minimal spanning tree is the specific spanning tree that has the lowest possible total weight among all possible spanning trees for that graph. In the real world, if you are laying down water pipes to connect neighborhoods, you do not need every neighborhood connected directly to every other one. They just need to be connected to the overall system. The minimal spanning tree gives you the absolute cheapest way to connect all the dots without creating any unnecessary loops. This concept leads us to how we write it down mathematically. We define a graph using a simple standard notation. G equals V, E. In this formula, the symbol G stands for the entire graph. The letter V represents the set of all vertices, which are our nodes or points. The letter E represents the set of all edges, which are the connecting lines. When we look at a specific edge connecting a node U to a node V, we write its weight as W of U, V. If the weight increases, the cost of that connection goes up. Building on that notation, we need a way to calculate the total cost. Here, W represents the total weight or total cost of our spanning tree. The Greek letter sigma means we are adding everything up. We are only summing the weights of the edges that we have actually chosen to be in our tree T. To solve the problem, we must find the specific tree T that makes W as small as mathematically possible. Crucially, if our graph has n nodes, any valid spanning tree will always have exactly n-1 edges. Adding one more creates a cycle, and removing one leaves a node disconnected. Now that we know what we are looking for mathematically, how do we actually find it? One famous method is Kruskal's algorithm. This uses what computer scientists call a greedy approach, meaning it always makes the most obvious, cheapest choice available at any moment. The rules are simple. First, you sort all edges from lowest to highest weight. Then, you pick the cheapest edge and add it to your tree, provided it does not form a closed loop. You keep doing this until you have exactly n-1 edges, guaranteeing the absolute minimum cost. Before we move on, let us see this with a concrete example. Imagine we have a graph with 4 nodes labeled A, B, C, and D. This means our total number of nodes, n, is 4. To connect them all without loops, we need exactly one less edge than the number of nodes, which is 3 edges. We are given the costs of all possible connections. Our first step in Kruskal's algorithm is to sort these edges from cheapest to most expensive. Our sorted list is AB, BC, CD, AD, and finally AC. Continuing with our sorted list, we start building our tree. We look at the first item, which is the edge connecting node A to node B with a weight of 1. Since our tree is currently empty, adding this edge cannot possibly form a cycle, so we add it. We now have one edge. We move to the next cheapest edge, which connects B to C with a weight of 2. Adding this gives us a line from A to B and B to C. This does not form a closed loop, so it is perfectly safe to add. We now have two edges and need one more. The next edge on our list connects C to D with a weight of 3. If we add this, our path goes from A to B, then B to C, then C to D. There are still no closed loops anywhere, meaning no cycles are formed. We add this edge. We now have exactly 3 edges, so we immediately stop. We calculate the final cost by adding the weights. 1 plus 2 plus 3 equals 6. This means 6 is the absolute cheapest cost to connect all 4 cities. Let us visualize the result we just calculated. On the screen, you see the 4 nodes A, B, C, and D. The solid blue lines represent the edges we selected for our minimal spanning tree: A to B, B to C, and C to D. Notice how every single node is connected to the network and there are no closed loops. The dashed gray lines represent the edges we rejected, like A to D and A to C, because they were either too expensive or would have created an unnecessary cycle. This visual perfectly captures our optimal solution. Now that we have seen Kruskal's approach, let us look at another brilliant way to solve this exact same problem, known as Prim's algorithm. While Kruskal looks at all edges globally, Prim's method builds the tree outward from a single starting point, much like a mold growing on a piece of bread. You begin by choosing any random node. Then, you look at all edges connected directly to your current tree. You find the absolute cheapest edge that bridges to a new, unconnected node and add it. You repeat this until every node is connected. Let us solve a new problem using Prim's algorithm to see how it differs in action. We have a graph with 4 nodes and we are given a new set of edge costs. We again need exactly 3 edges. We can start at any node, so let us arbitrarily choose node A. Currently, our tree only contains node A. We look at all edges connected to A. The available edges are AB with a cost of 4 and AC with a cost of 1. The cheapest option is clearly AC. Continuing with Prim's method, we add edge AC to our tree. Now, our tree has grown to contain nodes A and C, and we have one edge. Next, we look at all edges that connect our current tree to the outside nodes B and D. From node A, we can use edge AB, costing 4. From node C, we can use edge CB, costing 2, or edge CD, costing 3. Comparing 4, 2, and 3, the cheapest edge is CB. We add edge CB to our tree. Our tree now contains nodes A, C, and B. Finally, we need to connect the last remaining outside node, which is D. We look at edges connecting our tree to node D. From node B, we have edge BD costing 5. From node C, we have edge CD costing 3. The cheapest option is CD, so we add it. All 4 nodes are now connected, so we stop. Adding the weights 1, 2, and 3 gives a total minimum cost of 6. Prim's algorithm successfully finds the optimal solution, just like Kruskal's. So we have proven that these algorithms work. This brings us to why they matter. The minimal spanning tree problem is not just a theoretical math puzzle. It is the invisible backbone of modern infrastructure. Whenever a utility company lays down electrical grids or internet cables, they use these exact algorithms to save millions of dollars in material costs. In computer networking, it figures out how to route data packets efficiently without them getting stuck in infinite loops. Even data scientists use it in machine learning for clustering data points in facial recognition software. To summarize our lesson, the minimal spanning tree problem asks us to connect a set of points using the least amount of total weight without creating any closed loops. We explored 2 powerful ways to solve this. Kruskal's algorithm takes a global approach, greedily picking the cheapest edges overall. Prim's algorithm takes a local approach, growing the tree outward from a single starting point. Both methods are mathematically proven to guarantee the most efficient, cost-effective network possible. You now have the tools to solve complex network problems efficiently.